Let's see how we can use the average value theorem to calculate an average energy. To simplify this problem, let's imagine that we have a two-state system. That is, we only have two quantum states, a ground state with energy 0, and an upper state, E1, equal to epsilon. Each of these energy states will have a degeneracy equal to some number. So we'll just assume that both of these have a degeneracy of 1. In this two-state system, our average energy is going to be the sum, because we have a discrete system. Our states are not continuous, so it's not an integral, but we're going to use the sum of the energy for each state times the probability of that energy occurring, divided by the partition function. This is just the mathematical statement of the average value theorem. The first thing we need to do to use this definition is to find a value for Q. Remember that Q is the sum over all states of the probability, so this is just the normalization factor for our probability. To find the probability, we're going to use the Boltzmann probability. The Boltzmann probability is given by the degeneracy times the exponential of the energy of the state divided by the Boltzmann constant times the temperature. So for our first state, our ground state, the probability of the ground state is equal to the degeneracy of the ground state, which we have given a value of 1. So we have 1 times e raised to the minus 0 divided by kBt. And anything raised to the 0 is equal to 1, so 1 times 1 is equal to 1. So our probability of our ground state is equal to 1. This is an unnormalized probability. The probability of the first excited state is likewise 1 e to the minus epsilon divided by kBt. And so our partition function is equal to 1 plus e to the minus epsilon divided by kBt. And so at any given temperature, if we know the difference in energy levels, so we know what epsilon is equal to, then we can calculate a value for Q. So now our average energy expression is equal to the sum of the energy of each state times the probability, the Boltzmann probability of each state, divided by 1 plus e to the minus epsilon divided by kBt. To find the numerator in this expression, we do the same thing that we did to find Q. We just examine each state and then add the two terms together. So for the ground state, the energy is equal to 0, and so the first term is just going to be 0. The second term in the numerator sum is going to be equal to the energy, epsilon, times the probability, which is 1 times e to the minus epsilon divided by kBt. That whole thing is divided by Q, and so we get the following expression for the average energy of a two-state system. So notice that what we've done here is just apply the definition of the average value theorem to a two-state system. You can expand this to any number of states by just including more terms in your sum. So notice that as the difference in energy between the ground state and the upper state, so the value of epsilon increases, this fraction will decrease, because as epsilon increases, e to the minus a larger number is a smaller number, and so this fraction decreases. So the fraction of particles in the upper state will decrease as epsilon increases. And that makes the average energy smaller as epsilon increases. On the other hand, if the degeneracy of the upper state increases, then that will tend to increase the fraction in the upper state, because there's more ways to make the upper state, and so we're going to end up with more particles in the upper state. So as the degeneracy of the upper state increases, the average energy will increase due to the fact that you get more particles in the upper state. The more particles you have with higher energy, the higher the average energy.